All right, welcome to the explainer. You know that annoying camera bump on your phone? What if we could just make it disappear? Or what about something straight out of sci-fi, like an actual invisibility cloak? Well, that's what we're talking about today. A total revolution in how we control light. Let's dive in. So let's kick things off with a question. A big one that could honestly change every single device you own. I mean, forget that camera bump for a second. Think about those big, heavy lenses you see on professional cameras. Now, what if you could replace all that with a lens that's so incredibly thin, it's basically flat? I mean, practically two-dimensional. Okay, so check this out. On the left, that's your standard lens. Thick, curved glass. It works by bending light with its shape, the way lenses have worked for centuries. But on the right, that's the future. It's called a meta lens. It does the exact same job, but it's thousands of times thinner. We're talking just 100 nanometers thick. And here's the crazy part. It doesn't use its shape at all. It uses this amazing microscopic pattern on its surface to steer light. And believe me, that one little change, it changes absolutely everything. And look, this is way bigger than just making our phones a little sleeker. The tech behind this is called metasurfaces, and it's all about completely rewriting the rules for how we handle light. We're ditching bulky, curved glass for perfectly flat optics. And when you do that, well, you start unlocking things that used to be pure science fiction. I mean, think about holograms. By engineering a flat surface with these tiny, tiny patterns, we can project these incredibly detailed 3D images. And we're not talking about those blurry old-school holograms. These meta-holograms get rid of all that noise and distortion. The result is an image so clear, so high quality, it's something we've just never been able to do before. And that leads us to maybe the wildest application of all, cloaking. Seriously, look at how this works. You take an object and you cover it with one of these custom-made metasurfaces. Now, when light comes in and hits it, it doesn't bounce off the object like it normally would. No, the surface grabs that light and redirects it perfectly. It makes it look like the light just bounced off a simple flat mirror behind the object. And the result? For anyone looking, the object underneath is gone, completely invisible. Okay, so how in the world is any of this even possible? I mean, how do you actually tell light where to go with just a flat sheet of material? It sounds impossible, right? Well, let's dig into the core tech and see how it all works. All right, the magic word here is metasurfaces. Think of them as super thin 2D versions of something called metamaterials, which are basically materials engineered to do things that aren't found in nature. By taking that idea and squishing it down to a single ultra-thin layer, we can etch patterns onto it that are smaller than a wavelength of light. And when you can do that, you can control light with a level of precision that is just mind-boggling. And this is the key takeaway, the most important part. The secret sauce isn't the material itself. You can use something as common as silicon. The real power is in the structure. It's all about the tiny geometric patterns etched onto the surface. You can think of them like tiny little antennas, and just by changing their shape or how they're arranged, you can completely change what happens to light when it hits that surface. It's like programming light. And because it's all about structure, you get some huge advantages. Yeah, they're ultra thin, but they're also way cheaper and easier to make than grinding a traditional glass lens. This is what makes them so perfect for putting into the small gadgets we use all the time. Suddenly, we have this incredible toolkit to control every single property of a light wave. Its direction, its focus, everything. Now, this all sounds incredibly high-tech and futuristic, right? But here's the thing. We didn't invent this trick. Nature figured it out millions of years ago. And it uses this exact same principle to create some of the most stunning visuals on the entire planet. So this whole idea is part of a bigger field called nanophotonics, and it's exactly what it sounds like, the science of how light, or photons, behaves when it hits these tiny nanoscale structures. The big idea is that when you get this small, the physical shape of things matters more than the chemical it's made of. Structure is king. You've seen this your whole life. You know the incredible shimmering colors on a butterfly wing? Or the deep blues and greens of a peacock's feather? That's not paint, It's not pigment, it's nanophotonics. The color comes from microscopic structures on the surface that are shaped just right to bounce back specific colors of light. So yeah, nature gave us the blueprint. Our job is just to figure out how to copy it. Okay, that's really cool. But how do you go from a butterfly wing to mass manufacturing? How do you take these incredible, intricate designs and make billions of them for all our tech? Well, this is where it gets really clever. We don't have to start from scratch. We can actually use the exact same technology, the same factories, that build our computer chips. We can just build these nanophotonic structures on silicon wafers. We're piggybacking on decades of research and trillions of dollars invested in the semiconductor industry. And this perfect marriage of light and silicon has created this booming field called silicon photonics. And the possibilities are just exploding. We're talking about building the guts for super fast 5G networks, making data centers more efficient, creating the essential hardware for quantum computing and AI, even building the next generation LiDAR sensors that let self-driving cars see the world around them. It's everywhere. So let's be clear. This is not some far-off science experiment happening in a lab somewhere. This is a full-blown, multi-billion-dollar industrial revolution, and it's happening right now. Let's just follow the money for a second. We'll start with a new kid on the block, metasurfaces. Back in 2021, this was already a $305 million market. But that's not the story. The story is the growth. It's growing at nearly 37% a year. That's insane. That means it's on track to be a nearly $2 billion market by 2027. That kind of explosion is being fueled by huge demand from aerospace, from defense, and, you guessed it, from consumer electronics. And remember, that's just for the newer metasurface tech. If you look at the more mature field, silicon photonics, the numbers are even bigger. We're looking at a projected market of $4.6 billion by 2027. Think about that. It was just over $1 billion in 2021. This just screams confidence from the industry. When you see growth of over 26% year over year, that's not just a trend. That's proof that this tech is being adopted on a massive scale. And if we pull the lens back even further and look at the whole nanophotonics market, which is already worth over $12 billion, by the way, you see it's touching everything. It's not a niche thing. It's becoming a foundational technology that is changing the game in consumer electronics, healthcare, communications, cars, defense, you name it. So where does it go from here? Well, researchers are already pushing into some amazing new territory. They're working on flexible metasurfaces you could build right into smart wearables. They're creating new kinds of medical imaging that can literally see deep inside your body. They're even making optical tweezers, using beams of light to physically grab and move around individual cells. It's just incredible. Honestly, we've only just begun to scratch the surface here. This is a technology that gives us this almost godlike control over light itself. From making things invisible to revolutionizing how we see the human body, the possibilities are staggering. And it all leads to one really big question. Now that we have the power to control light, to literally engineer reality, what will we choose to see next?